So let's start with Sibylle's talk. She will tell us about Jordanian crystal strings and spins, please.
Thank you. Yeah, so first let me start off with the obvious, which is thanking the wonderful organizers here for giving me the opportunity to speak and also for organizing this, I think, 5th edition. It's always very exciting every summer to go to this conference, and so I'm very happy to be here. So I'll talk indeed about Jordanian twisted string theories and spin chains, and I'll focus on their integrability and how we can use their integrability to study the spectrum of these models. And along the way, I'll show you many of their nice features and physics. So this is work I've been doing in the last few years, mostly with Riccardo Borsato at the string side, but now more recently also with Fedor Levkovich-Matyuk, as well as Adrian Molin, who is my student at ETH. And he's really doing the heavy lifting here on the calculation of the spectrum. He also has a poster on Thursday, and I really advise you to have a talk with him because I think he will be very enthusiastic to talk about this. So, all right, before starting, let me, sorry for the banner over there.
Maybe you can just press OK.
Yeah. Okay, before starting, let me just remind you of why we like to have integrable models and use integrability. Basically, this comes from the very ambitious goal that we have to have exact control over quantum field theories at any coupling. And we know that integrable models have been great to in that respect. In fact, in 2 dimensions, it led to some fantastic milestones of having an exact mass cap for certain sigma models. And yeah, this was being done in the 90s, only has a few citations, which is quite remarkable. But in any case, it's quite a remarkable result. And going beyond 2 dimensions for the moment, we have also some very nice things going on, especially in the context of ADS-CFT. So we can have in mind basically in that context to have some 2-dimensional integrable string world sheet theory, some interacting QFT that gives rise to some gravitating spacetime, which is dual to some quantum field theory in higher dimensions than, possibly higher dimensions than 2. And this integrability of the world sheet you can think of as sort of transpiring further and leaving some marks in the dual QFT, in particular in terms of the spin chain in the cases that we know and love. So this now doesn't work anymore. Okay, so the most nicest example, let's say, is the ADS5 CFT4 correspondence in the planar limit, where we had an exact planar spectrum of a 4-dimensional QFT. Due to many people around and many pillars also here in the room. So what the story is here is that basically you have some integrable spin chain that underlines our ADS-CFT duality, where on one side we have some string propagating in a maximally supersymmetric target space, ADS5 is 5, and that is dual to this 4-dimensional quantum field theory, which is NS4 Cyprian-Mills. And also this guy is quite symmetric, so we have, in both cases, we have maximal supersymmetry, and also the gauge theory has some CFT, all gathered in terms of some PSC2,2/4 group, and as well we have integrability in this spin chain underlying it that allows us to do this exact computation. So it's quite special, and this is actually nice because we can use all these special symmetries to ask questions such as, can we sort of slightly deform away from this and possibly get some new integrable structures, some very different integrable structures. And if they are very different, then perhaps we can learn more about the physics at any coupling, some new things about the physics of it. So this is sort of the motivation that I have. And in particular, I think there's some very nice algebraic story that has been sitting in our labs. Basically in terms of the formations of spin chains, which is mathematically under great control, and there's some nice algebraic control, and it goes through the name of Drinfeld twisting the spin chain, or Drinfeld twisting the integrable Hopf framework. And basically, already Niklas has introduced this in the morning, there's a there's some co-product structure of some symmetry, some infinite dimensional symmetry that can get twisted. And we also have a universal R matrix that allows you to do the integrability studies that will get twisted. And in fact, this type of deformation of the spin chain has been conjectured by Stein in 2015 to correspond to a deformation of the string world sheet that is known as a homogeneous Stein-Baxter deformation. And so, yeah, in many of these cases, it sort of kind of mildly deforms the integrability and the story. But in some cases, we will get some truly different things arising. And the Jordanian model that I will talk about now in this talk will be one of those cases. So here is sort of the picture that I have. We have the deformation of the spring world sheet in terms of deformed interaction, so meaning that it deforms into the deformed target space. Then on the gauge theory side, the Driezen twisting of the spin chain will transpire into some possibly non-commutativity of the gauge theory and give you some very different model. And as I said, the Jordanian class is basically a class of homogeneous Yang-Baxter deformations, and they, as I will try to argue, will really force us to rethink about what ADS-50 integrability really means and how we can discuss some different aspects of it. Okay, and in particular, I will be focusing on these two corners. So sorry, the pointer doesn't work anymore, but I'll focus on the string and the spin chain. Good, so that's a rough outline. Yeah, but yeah, as I said, I'll talk about integrability from the string theory, and then I'll talk about the spectrum from the spin chain. But first, before doing that, let me just introduce to you what is a homogeneous Stein-Baxter model. So basically, it's an integrable deformation of a two-dimensional sigma model with an isometry group G. So in the case of a string propagating in S5 as 5, this isometry group will be PSU 2.2/4. And our specific details don't really matter, but just to show you, we have an action principle that realizes this deformation. And the thing to focus on is the object eta R, which is sitting in that action, and it has a bunch of nice properties. So eta is just a parameter, it controls your deformation. And then we also have an operator R on the Lie algebra of PSU 2.2/4, and that satisfies these three conditions that you can see here. So we have the classical Yang-Baxter equation for R, and also R should be antisymmetric with respect to the algebra of PSU 2.2/4. And then it also satisfies, has to satisfy some unimodularity condition with respect to that algebra. And using these three properties, you can show that the world sheet theory or this action will be integrable, and also the target space it gives rise to will solve the type 2B supergravity equations of motion. So that's quite nice. Now, in fact, it is conjectured, or what do you say? It corresponds to a Driezen twist also, having these type of properties. In particular, I will go into more details later, but a Driezen twist at the classical level here is some deformation in terms of precisely an object that satisfies these type of conditions. And the solutions to these conditions, yeah. Thank you.
You have to use one concentration slides and one for the later.
Okay, perfect. Yeah. Yeah, I'm very used to normally using pointers, so. Okay, great. Okay, so here, the three conditions. Good. So they have a bunch of solutions, and these solutions, we have classified them for PSU 2.2/4. And we will see that you basically have a whole range of family of possibilities that you can choose from. And that is quite good because, yeah, the integrability and having these supergravity sort of shows or tells you that you could have some type of holographic interpretation. Now, let me just try to very, very roughly divide all the solutions in, in two type of classes, which are known as TC transformations or the Jordanian transformations that I will talk about. So TC transformations, it's basically based on abelian T-dualities. They correspond to doing a T-duality, a shift in a T-duality, and you do that over some abelian subalgebra of your isometry group, PSU 224, and that corresponds to doing some Yang-Baxter deformation over this abelian subalgebra as well. So the image of this R operator now will be spanned by some commuting algebra of H1 and H2 generators. And you will, well, so these commuting generators, they could be Cartan, they can also be not Cartan, in the sense that they can be non-diagonalizable, but in any case, they should commute. And then you can check what symmetries are related after doing this transformation. And you will find that it always includes the commuting charges, generators, as well as the centralizer of this image of R. So this relates to basically the type of models that Nicholas has been discussing this morning, where you use this to also Drinful twist your theory. Now, what happens to the integrability structure is kind of nice. In some cases, nicely understood. Basically, it sort of changes all your spectral equations using the charges of your fields that are charged under these generators that you use for the deformation. Okay, but the Jordanian classes will be quite different and less understood. Basically, they are equivalent to doing a non-abelian T-duality transformation, and they are done over some non-abelian Borel subalgebra of isometries. In this case, the image of R is spanned by this Borel subalgebra, which is itself in an SL2R subalgebra of PSU224. So H and E here satisfy this commutation relation, where H is a Cartan of SL2R and E is, for example, a raising operator, so some root type of generator. And the remaining symmetries, or the key point maybe from this slide is that the remaining symmetries for Jordanian deformations, they will never include this Cartan, rather, so that's opposed to what we have at TCT, they always include the Cartans. But here we will never have the Cartan in the residual symmetries. We do, however, always have this root generator as well as a centralizer of this algebra in PSU224. Okay, but before using that fact, let me just continue with my super rough overview, which is just giving you some type of backgrounds that you probably recognize. So all these type of backgrounds, the Lunin-Malacena, Schrödinger spacetime, Hashimoto-Izaki-Madasena-Russell background, they are all homogeneous and Baxter deformations. And in fact, they all correspond to TST transformations. So on the other side, we have the non-abelian deformations, where I think there's some names. So in particular, this shows that there's less understood. It doesn't have a fancy name yet. All right, so now I use this. Yeah, okay. Good. In particular, what also happened at the gauge theory side in the case of the TST is also quite nicely understood. So here for the Lunin-Malacena, you would take these commuting generators in SO6 or in the sphere. You're basically not deforming ADS spaces, and that will correspond to some marginal deformation of your gauge theory. So this is known as a beta and the gamma deformation. And then you can also take the commuting generators in SO2.4 so that you deform ADS, and then you will get some non-marginal deformation, and in particular, you will be deforming the space-time symmetries of this gauge theory in terms of some non-commutative structure. And those are known as dipole and Grunwald deformations. Then the Jordanian cases, because they have this, the generators participating are in this SL2R, they will deform the ADS spaces, so they should be some non-commutative deformation. But what is precisely known in that case is very unexplored terrain. However, there is possibly one possible, there is one possible background that I think should deserve a bit more attention and maybe get even a nice name, even though like they have maybe a bad reputation because they correspond to non-abelian T-duality. In fact, there is one class of Jordanian deformations where you should have some nice properties, and it will be the one that I will be discussing. So in fact, the background related to this unique case, let's say, has some constant dilaton, so that gives you confidence, and it also still has a type 2b supergravity. So in this case, the H and the E generator, they are very specific. So they're this combination of the dilatation, H is a dilatation operator sort of boosted with J03, and then E is a combination of the momentum generators of SO2.4. Okay. And as I said, in the residual symmetry algebra, you will always have the E generator appearing. So these are all the residual symmetries. So out of the 15 generators of SO2,4, we will have 5 generators. One of them is E. And then we have all these other ones which will commute with E and with H. And then if you stare at this long enough, you will also find out that there is also some other SO2R subalgebra in this residual symmetry algebra. It will not be super important for my story, but what is nice is that it actually relates to non-relativistic CFTs, where the boosted dilatation operator that you have here corresponds to some non-relativistic scaling dimensions. And then the other elements of SL2R, they will define non-relativistic descendants as well as a state operator map in the context of non-relativistic CFTs. And it's also known as a Schrödinger algebra or a one-dimensional non-relativistic CFT. Anyway, so in this residual symmetry algebra, you can start thinking of how you should look at the spectrum of these models. And you do that typically by looking at the Cartan of commuting generators. In the usual case, which is a bit small here, you take the, you have some nice diagonalizable Cartan generators where we have some angular, well, some rotations in the 3-4 plane of ADS that correspond to some spin. So we have that in the 3-4 plane and in the 1-2 plane. So you have 2 spins. And then you also can choose either a timeline generator, which is P0 minus K0, or a dilatation generator. So some radial type of types, which are related as in the usual case with the state operator. Now here, this will be quite different. So we will have 3 different commuting generators. One of them will be this E generator. It's not diagonalizable, but basically sort of corresponds to momentum. In the usual case, momentum is not a diagonalizable, it's not associated to a diagonalizable generator. And then we also have some spin angular generator. And then again, we have 2 choices, either a timeline generator or this radial generator, which are the non-relativistic versions of the usual case. Okay, good. And then you can write down the type 2 supergravity solution. The coordinates related to these abelian shifts, I will represent them by theta, t, and phi. So t for time and related to energy, and phi, I don't know for what, but related to this momentum. And then also the angular coordinate theta related to the spin. Yes. Yeah, thanks. So I didn't talk about it, but basically you have to, well, for supergravity, you have to add some additional supercharges and everything, and this will also affect how many supersymmetries that you have. But at the end of the day, you will have, if you do it nicely, you will have 12 supercharged out of the 32. All right, good. Okay, so now that I introduced the model and the string aspects of this, I can talk to you about the S matrix story. And I'll try to be brief. I don't have that much time. There's also not much to say, basically. The key point is here that because we're sort of severely deforming the target space, we're losing a lot of the symmetries that you would usually use to start looking at your scattering problem. In particular, you have to take a particular gauge that identifies the asymptotic states that will scatter. And in the usual case, you will take the gauge that will leave the most amount of symmetries after the gauge fixing, so that your gauge fixed model is still good and you can actually do calculations. Now, this depends on what type of symmetries that you have, which gauge that you choose. And in the Jordanian case, this nice gauge, which is also for the people that know, the nice gauge would be the one that gives you the PSU2/2 squared symmetries on the gauge theory. This nice gauge will not be present anymore after the deformation. Not be possible because you don't have the symmetry. And so you're forced to do another gauge fixing. Yeah, I can talk more about this, but I won't. But anyway, yeah, just having that in mind, what you then do to study the scattering problem, and this will be important, is that you need some point-like solution on which you do this gauge fixing. And for that, you need to look at sort of the simplest possible point-like solution that you can take, where you also turn on some non-trivial charges for your coordinates. So in particular, we can turn on energy for the timeline coordinate, We also turn on this momentum M, and then we can also turn on an angular momentum in the sphere J. And then we can turn off the spin of ADS. So just to get the simplest possible case. And then you'll find that these charges E, M, and J are related by the Virasoro constraint in this way. And looking at this, so in an ADS CFT interpretation, what is sensible is basically only the large angular momentum contributions, because you have to go to some semi-classical regime where the charges are large. And then you'll see that you get a deformation of the usual BMM operator. And the deformation is governed by this momentum charge and that you turned on. And also eta, of course, the deformation. Okay, good. So you use this solution, do the gauge fixing, you get a new worldsheet Hamiltonian. This new worldsheet Hamiltonian will have different symmetries than usual. We'll have some SO2 common and SO2 subalgebra. How it precisely looks like is not important, but what is important maybe is that this subalgebra contains this H and this E generator that you use to do the Jordanian deformation. And for that reason, you could ask, well, okay, so maybe I could use these symmetries to also do this Drinfeld twisting of the S matrix. So I told you before, a Drinfeld twist will sort of change your R matrix in this way. And the R matrix is roughly related to the S matrix if you want. And so you could ask, is the S matrix also Drinfeld twisted? So let's check that by doing an explicit computation. So at tree level, you can look at the scattering problem. You take this gauge, obtain the perturbative Hamiltonian, and you expand in the all the possible fields that will scatter with each other. And you will get some, in this case, you'll particularly get some cubic contribution part in the Hamiltonian, so some 3-point vertices, as well as higher point vertices and everything. And then you'll see that, well, from the quadratic Hamiltonian part, you can read all the dispersion relations, and you will see that you find this, which are some nasty non-relativistic dispersion relations. And this basically means that you cannot use normal kinematic rules to, for example, rule out cubic processes. Okay, this you can normally do when you have relativistic dispersion relations, but you cannot do it when you have non-relativistic dispersion relations. And you'll see that, in fact, then the cubic Hamiltonian will actually physically contribute to your scattering problem. You'll get some particle production processes, which I listed here, and they will involve massive asymptotic states. And for the people, the experts, usually this is quite a bad sign. It basically says that you have inelastic scattering already at tree level. And this, well, usually if you encounter that, people would sort of throw away this quantum field theory and then throw it in the bin, because it basically is violating the axioms of S-matrix integrability and, yeah, jeopardizing the methods and the tools that you can use based on factorized S-matrices. It also questions of if we really have this Drinfeld twisted correspondence. But okay, I will try to argue that everything is actually fine. So, good. So in particular, the reason why we look, why we think we have some Drinfeld twisting, let me just briefly remind you of that. It comes from basically from the Lax description. Try not to go into too much details, but
sorry.
Yes.
Those vertices were non-zero on shell.
Yeah. All right. Good. So we have sort of a nice Lax integrability description where we have two sort of pictures where either you have a deformed Lax connection, but closed fields, periodic fields, so some closed strings, and therefore propagating in some, well, you have a deformed Lax and a deformed interactions and deformed spacetime, etc. And on the other hand, you can also reformulate this in terms of some undeformed Lax connection, but where the fields get twisted under the deformation. So you have some sort of special type of open strings that have a twist that carries all the information of the deformation. And to travel between these two pictures, there's basically an object F, which is sort of a classical version of a Drinfeld twist. And so what happens is that you can look at the deformed Maloney matrix of the sigma model, which is this path of the exponential of your deformed Lax connection. And you'll find out that you can sort of strip off this F object, which carries the deformation, and you can strip it off in this way, sort of a gauge transformation way, where you have a Bayes transformation of the undeformed Lax connection. And this is a classical Drinfeld twist, as we saw earlier. Now, we've written down some years ago explicit expressions for all possible homogeneous ambidextrous deformations, so for abelian or TST and also Jordanian deformations, where for the experts you can really recognize the usual Drinfeld twist of spin chains, which are in this case called Drinfeld-Reshetikink twist, and then here also just Jordanian Drinfeld twist. So that is the reason why we believe this, coming from Stein, and then it sort of gives this first indication that we have this twisting of the spin chain. Okay, so how am I doing with time?
I still have 20 minutes.
Oh, amazing. Okay. Okay, good. Yeah, very nice.
No, sorry. 12. Well,
20 plus
I heard
question.
20.
I'm not sure when we started because there was.
We're 5 minutes. Yeah.
Anyway,
You have some time.
good. So yeah, let me now go to the Drinfeld twisting of the spin chain and calculate the spectrum and tell you more about that. Okay, so first, let me tell you what is this relevant spin chain that we have to look at. I'll give you the ingredients of the spin chain. Because we're gonna do a Jordanian deformation, the relevant spin chain will be Heisenberg XXX spin chain in the infinite dimensional -1/2 representation, basically just the relevant guy for the SO2R sector. So we imagine that we have some chain of particles that are in this infinite dimensional spin representation. So it's just not just like spin up and spin down, but it goes on. Good, and this system has some Yangian symmetry, as already discussed. Some Yangian symmetry, in this case for the SL2R sector, and Yangian of SL2R. And basically how it acts is governed by this co-product delta of X. So we have X in this Yangian, and then the co-product will distribute this on all the sides of the chain, and how that is acting on the system. All right, and this what is nice is of course that we have some R matrix underlying this spin chain. In some representation, the simplest maybe it looks like this. So here the small j will be my physical spin chain sites, and then j I will use for physical sites, and A will be some auxiliary space that could be, if you want, finite dimensional. So in this representation it will be, and then these are just the Pauli matrices in the finite 2x2 representation. But importantly, in the physical space, you will have this non-compact representation, so some infinite dimensional representation as J, which in terms of SL2R can be represented like this as differential operators in some continuous parameter set. And then the wave function will depend on these continuous parameters. Good, and as we all know, from this R matrix, we can build the monodromy matrix, which is just this product of R matrices over all the sides of the chain. So big J will be the length of my chain, and this guy encodes the commuting operators of this system. Okay, now if I would take this auxiliary representation also in the physical space, you can also find your physical Hamiltonian of your spin chain. How it precisely looks like doesn't really matter. I will give a representation also later, but it's basically related to the R matrix in the physical representation through this relation. Okay. All right, and so then you can Drinfeld twist this system, and what does that mean? So you need an object that satisfies this condition, which is called the co-cycle condition. And if you do that, you can sort of twist all of the structures that underlie integrability. So in particular, you have the co-product that gets twisted in this way. Then the universal R matrix gets twisted. Because of that, also your monodromy matrix will be twisted, and also your Hamiltonian will be twisted. All right, and so this, because of the co-cycle condition, it gives you a lot of algebraic control, and you will see that after doing that, you will still have what is called a quasi-triangle Hopf algebra. Basically means that you have the Baxter equation or TT relations that you can use to study. Now with Adria, well, I want to emphasize that we had some very nice formula for the twisted monodromy matrix, which is really independent of what type of Drinfeld twist that you choose. And it looks, it is this formula here. So basically we have sort of a similarity transformation by an operator omega, which is, I didn't write it explicitly, but it's basically an operator that is constructed out of the Drinfeld twist on all the physical sides. So it's just a physical sort of action. And you can get rid of that by doing a similarity transformation of your Hilbert space. But then what is important is what is in orange. So it's this iterated coproduct of the Drinfeld twisted F matrices that are twisting your monodromy matrix really. And similarly, you can do that for the Hamiltonian. For some specific cases, the twisted Hamiltonian has been explicitly written down by these people for TST and also for Jordanian cases. And then again, you will find the same similarity object appearing and sort of a twisted version of the Hamiltonian H star. Okay, good. All right, so now let me go to the explicit Jordanian Drinfeld twist. It looks like this. So again, we have this cartan of Esaltoire appearing, HI, and then also the root generator E. Now my deformation parameter will be psi. It will be related to the eta deformation parameter, well, through some relation that I will show you later. And so, yeah, this is sort of the relevant object, and you can already see it really looks the same as in the sigma model, where you also have this log term appearing. Okay, now then if you want to use RTT and all these things to study your spectrum, it will be really important to look at what are the manifest symmetries after doing this Jordanian twist. And so as I said, the co-product is telling you how the symmetry operators are acting on your chain. So what you need to do is look at this twisted co-product and see what generators are commuting with your twisted Hamiltonian. Now, because there is basically a similarity transformation given, yeah, okay, so here also the full twist co-product will have this similarity transformation, and basically this is equivalent to look at the normal co-product of the generators and how it's if it's commuting with this twisted Hamiltonian or not. And what you will find for the nice level 0 algebra generators in Esaltoire is that very much like the sigma model, that we always will have this root generator being a residual symmetry. And I will denote that by M hat, which is this co-product of E. And it will never have a Cartan generator, so the H Cartan generator in Esaltoire. So, oh, no. Now the laptop still works. Okay. All right, and so this means that if I need to organize a spectrum according to manifest symmetries, I will have some continuous spectrum for this this root generator because it's this non-compact generator, and I won't have any discrete spectrum that you usually have when you work with a Cartan generator. So this is like this discrete spectrum that you would usually have, and then you would use to like look at the beta ansatz and the beta states and everything. Okay, then the explicit twisted monodromy objects will be this thing. And what is important is then for the specific Drinfeld twist, what is nice is that the object that is acting on your states, so this monodromy matrix has to act on the states. So this object here that is acting first will be governed by this residual symmetry generator. So after doing the similarity transformation by stripping away omega, we see that we can organize our spectrum according to eigenstates of the root object, root generator. Okay, so then we also looked at the twisted picture for these Driezen twisted chains. With that, I mean that you do a Driezen twist, and you can also, much like the string worldsheet, you can reformulate the problem by an undeformed spin chain with undeformed interactions, but twisted boundary conditions. And I won't go into the details, but basically I will just give you the results. So now we can look at the generators that are acting once you pass through the spin chain. If you go one time around, it will pick up some twist. And the result is that the twist will again be the same object that was appearing also in the twisted monodromy matrix, this thing, which in particular is governed by the M hat symmetry charge, and explicitly in terms of SL2R generators to get these twisted boundary conditions in terms of M hats. Okay, good. And both these things, both the twisted boundary conditions as well as the twisted monodromy objects, so the formulas for them, we were able then to use these guys to study the spectral problem. And so I will discuss that now. So first of all, we looked at the thermodynamic limit by taking the length of the chain extremely long so that you can get some field theory results from classical field theory. Then the other regime is a very small chain of size 2. And then we also obtained results at any length chain. And this is unpublished, by the way. So yeah, I didn't mention that, but there's 2 papers and one of them should appear soon together with Fedor. Okay, so first, let me discuss the thermodynamic limit. The story here is that you sort of start with an undeformed Hamiltonian in this twisted boundary picture, so undeformed interactions. You can take some continuum limits, and what you recover is a sigma model, basically, which is called the Lambda-Lifshitz model. And the fields of this model are these N, H, and E, and F, and they're related to these SL2R generators in some coherent state representation. And then you can look at how these, using these twisted boundary conditions of H, E, and F, you can look at how the fields are also twisted. And you'll find this particular expression where, again, this M, the continuum version of this M generator reappears. Then looking at solutions of the equations of motion of this sigma model with these boundary conditions, we actually find some solutions that have minimal energy. And these are given, this is written down here. And if what is nice is if you rewrite this in terms of the sigma model variables and you expand that large angular momentum, as I said, that is something that you need to do if you want to go to the string semi-classical regime. If you do that, we find an exact matching with the Virador constraints that we had for deformation of this BMN operator that we had earlier. So this is quite nice and gives us a lot of confidence because now we really have a matching between like a Greenfield twisted spin chain and the classical string energy at large angular momentum. So it seems that we're doing the right thing.
Bill,
yeah.
Do you expect them to disagree on the first term?
Yeah, so basically you should think of this as the E string equal J is like the vacuum. It's like your anchor points that is 0, and here maybe I should put a prime or something, but the ELL should be E string minus J.
Thank you.
Good. All right, and so as I said, we were happy with that, and this gave us confidence to look at the length 2 spin chain. So the key point here is, well, now what we will do is to use the twisted monodromy matrix, and the key point is that we will have to work in the eigenbases of M hat, and not in this discrete Fock space that you usually use for beta ansatz. Nevertheless, even though it's a root generator, it's basically momentum, right? So it's related to this E guy, which was here, which is really just you can represent it as some differential momentum type of generator, and you can write down an eigen state for that, which is of this form. So the charge n is here, and then the unknown function is g. And then you can say, okay, I can look at the twisted monodromy matrix now, which for length 2 will look like this. And you can diagonalize this as a differential problem on these eigenfunctions. So all of these are differential operators. And so what you need to do is solve some differential equation. For length 2, it's feasible as long as you use Frobenius. In general, we didn't really know how to do this without using Frobenius. but basically you can expand around some regular points and you can find a solution for this unknown function and also for the eigenvalue of this transfer matrix. And so we find here that, well, it will be some degree 2 polynomial with some specific coefficient that's u squared, and then some series and the deformation parameter psi that we went up. Well, basically we can go to arbitrary high order, but we just explicitly copied this one. And the point is that well, you will see that the spectrum of this eigenvalue will be deformed, and this is one lesson already because this goes kind of in contrast to what has been done before, where an undeformed spectrum was found when you were working in this Fock space of Cartan states, which you can still do, of course, but what happens here is that you really get some sort of the spectrum, the Hamiltonian becomes sort of Jordan block, and I think this is also the reason why people call this Jordanian deformation. But having the Jordan block, I think, obscures what is happening to the spectrum in terms of the generalized eigenvectors that is related to that. And in particular, also some of these Fock states will have some zero momentum because, of course, the momentum is some root generator. So if you would have an eigenvalue, then it will be a zero eigenvalue, and then you will not find any deformation of the spectrum. Okay, anyway, let's get to the nice things. So we then were able to use the eigenfunctions of this transfer matrix to find the spectrum of the Hamiltonian. So here now I give you some representation of the Hamiltonian in terms of some integral on some eigenfunction, on some functions. And so this representation is nice to use for us in this differential operator representation. So we can explicitly calculate what happens when you do a Drinfeld test. And then we will see that the eigenfunctions of the transfer matrix will also diagonalize the Hamiltonian, and then we can read out the energy. And basically, is this thing. So this is good. Then the next step, what you can do, is what is called Baxter TQ relations to then really go and calculate the spectrum in various corners. So Baxter TQ relation is this particular relation. It sort of reorganizes the spectral problem in terms of Q functions. It has its roots in beta ansatz computations, but it also follows from Yangian representation theory. And basically, it's expected that for any rational model like XXTech, the TQ relation should look like this. And then you can rewrite the energy in terms of these Q functions. And the nice thing is that using just some analytic ansatz for these Q functions, we can, and as well as the eigenvalues for these twisted transfer matrix, we find the energy that is precisely obtained from a direct computation of the Hamiltonian. So that is quite cool because it says that we can really use the machinery, the analytic machinery of the TQ relations to study the spectrum. So we have strong evidence that this is the right thing. In particular, we can then go beyond length 2, for example. But first, we can even do more than within length 2. So Baxter equation is something extremely powerful. It can sort of reproduce even the eigenvalue of the transfer matrix by just plugging in some generic ansatz as well as an ansatz for the Q functions. And then doing that, you can sort of use numerics and go to very high orders in the deformation parameters. So here, the plot is for the energy of the ground state with the deformation parameter repackaged in terms of this phi. And the pink thing is some analytic results corresponding basically to, well, to this object here. But then you can use numerics to go very, very high. And we also generalize these to other spin states. And in fact, maybe the nicest thing, which is the thing I will end with, yeah.
In this denominator, the numerator seems to be like the Casimir.
Yeah.
The denominator is some proof theory.
Maybe, I don't know. So this is just from pure closing eyes and just doing it. But yeah, it looks very, and would be nice to understand. Yeah. But I don't know. Okay, good. So now then we were also able to use Baxter equation to study the spectrum at all lengths. So basically what you do for that, I think I'm going over time, but you're looking at you can use the asymptotics of the twisted modernly or twisted transfer matrix and also come up with some good answers for this guy as well as the Q functions, and then you can just solve the Baxter equation and compute the energy for various data points. So for j equal to 8, and basically you can go very high if you want. And right, okay, maybe I should also, by the way, this is really Adrian's work, and also here he was also very strong in doing this. Should probably mention it. So you get some all J expression by just sequencing and fitting to this data. And the remarkable thing is then that you can look at the large J limit and try to see if you actually get a match with the ground state energy of the string calculation. And in fact, we do. So at large J, repackaging in terms of sigma model variables, we again get the same contribution as we had from the Lana-Lifshitz result, but here really coming from Baxter TQ. And we also get some quantum correction to this, so this is a ground state energy, and so this is basically a one loop shift of the ground state energy, and that precisely matches with computations that we did on the string theory side with Ricardo and Juan Miguel Neto Garcia and Leander Ruiz and a few years ago. And so this is again quite a nice match between the string and the spin chain. So we're very happy with that, and this allows me to basically conclude. So I've discussed a little bit about the Jordanian string theory, which is Lax integrable in sort of two ways. So it has this deformed picture and a twisted picture. And well, I didn't mention that, but basically using that, we were able to do these spectral curve results that we had with Ricardo and etc. And so get this data from there. But then looking at S-matrix integrability poses a lot of questions. So in particular, we have particle production processes with massive asymptotic states. So what does that mean for integrability? Can you use TVA on the string theory, etc., etc.? This is quite unclear and would be interesting to understand better. But luckily, it seems that we can still do a lot. So in Drinfeld, for using Drinfeld twisted spin chains, we were then, well, first of all, we were able to write down some general formulas for the twists of the integrable structure. But then we were also able to use that to study the spectrum. It was important to work with some residual symmetry states. In particular for the Jordanian case, this was in terms of some root generator and not a Cartan. And that allowed us to study the spectrum using the Baxter equation. We get some quite nice results. So for length 2, I have good numerics and perturbative results in the deformation parameter. Then we also have the all length thing that allowed us to match with the string theory. And so then, yeah, there's a bunch of other questions that you can ask and can do to push this further. But maybe the key thing that I want to end with is perhaps this shows us that particle number in the sense of like really as scattering states, but also as Fock states, maybe they are not always a good organization for doing studies of integrability. And you should actually be quite happy with that, because, well, at least I'm happy with that, because it tells us that we can have a nasty QFT with particle production processes, which you normally would just throw away and not care about, and be like, okay, this is too hard. But here we see that we can still, even though we have that, we can still use other structures of integrability and really study this, and this does then give us a lot of hope to even tackle even strong harder quantum field theories in the longer term. So yeah, with that I want to end then. Thank you.
Are there any questions?
So any idea of what should replace factorization of scattering as a definition of quantum integrability in this model?
Yeah, so in this case, it's basically just not like a scattering of particle number states, but scattering of different types of states that are these, I don't know, like these type of momentum type of coherent states, if you want. It's a bit like physically unclear, but at least for integrability and using integrability, it seems that you can still have some, well, nice twisted factorized R matrix, right? That is still satisfying in a Baxter equation and that you can still use to study things further. And it's not really like at the string, this is a big question that we want to address at the string world sheets. How should I think of it? Yeah. But any idea, probably it should be related to these different states.
So the naive physical S matrix that we would compute is not allowed.
Yes. Yes, yeah, that's the message. Yeah.
Possibility is just instead of expanding around this essentially near PP wave, you should just define your particles differently in a sense. Is that the idea, or?
Yeah, that's unclear to me.
I mean, there are some theories where you look at the Lagrangian, and if you look at that field that appears in the Lagrangian, that would not be the nice field to look at for integrability, right?
Yeah, and sort of intuitively, probably yes, but at least like practically, if I need to do the gauge fixing and take a particular solution, we were really forced to only one choice, in the traditional lower sense, like how you would usually do it, and there it was not working. But yeah, maybe there's some non-local reformulation of the problem. Again, in terms of these weird states, we have big question marks, but.
Can you comment on interpretation of this spectrum in the 4D theory? It's not quite CFP anymore, right? Once the definition is turned on, how should I think of these getting dimensions?
Yeah, another big question. I would say I don't know, because as I said, this gauge theory will be some non-commutative version. And also there it's the physics of the operators and everything is a bit unclear to me at the moment. But I would definitely. Well, it's in the usual story you can really say like, okay, it's this operator, you have this charge, this spin, whatever, and this is really obscure to me for the moment. But at least at the level of the spin chain, you can say and study a new model.
Maybe Tim, a quick.
Yeah, I can maybe comment on that. Like, so the first thing is that it's really, as Sibyl said, it's really hard to define these non-commutative versions with Jordan twist. Actually, it's not understood how to define these compatible with gauge symmetry. And then the other thing is that I mean, you're right. In principle, you wouldn't expect the normal dilatation operator to be the right quantity where you would find some spin chain integrability. But in principle, what could be thinkable is that you do some add some charge or something, so that in the end you get some effectively nice quantity that you can do some anomalous dimension calculation. That's the rough idea.
In view of time, I would suggest postponing all further questions to the coffee break, but first let's thank her again for the call.